Hello everyone, I just wanted to show you an example of using JUMP's distribution calculator to calculate probabilities and um, cutoff points from a normal distribution and work in some ideas about the central limit theorem with this as well. So let's suppose, for example, we have in a certain human population cranial length that's approximately normally distributed, and it has a mean of 185 millimeters and a standard deviation of 12 millimeters. So a couple of questions that we might want to answer with this is a question about individuals. So what's the probability that a single human draw from the population has a value greater than 190? And this is one that we're familiar with already. But another question we might want to answer is about means. So if we drew a sample of size 25, what's the probability that the mean of x is greater than 190? So an important distinction between these two questions is the first one is about an individual. The second one is about the mean of those 25 draws. And so we need to know something about how that mean behaves. And the central limit theorem tells us that as long as n is large, as long as the sample size is large, then that mean will follow a normal distribution. So we can also use the normal to help us calculate that probability. So let's look at these probability calculations in turn. In this first one, we want to calculate the probability that x is greater than 190. So I can standardize this, and that's the probability that x minus mu over sigma is greater than 190 minus 185 over 12. So that becomes the probability that a standard normal random variable z is greater than 5 over 12. So that's the probability that the standard normal random variable is greater than 0.416 repeated. So now I can find that from my distribution calculator in JUMP. From the JUMP home page, I'll select Help and the Sample Data menu. Under Teaching Resources, we'll go to Teaching Scripts and Interactive Teaching Modules, and then we'll locate the distribution calculator. So I'll just minimize these screens in the background so we can just see this distribution calculator. I'll have the normal distribution selected, standard normal with mean 0 and standard deviation 1. And I want the probability that z is greater than the quantity that I put in here. So I'll select that option, and I'll put in 0.416666. And that shows me that area graphically and tells me that that probability is 0.3385. So not only is there 33.85% of the area above 0.416 from the standard normal, but there's 33.85% of the area from a normal centered at 185 with standard deviation 12 that's above 190. So we just found that same thing, and we can check that here if we want to. We can put in the mean of that normal distribution of 185 with standard deviation 12, and then I'll put in 190 for the value that I want it greater than, and you'll see that we get the same 0.3385. Okay, so let's look at this idea with the central limit theorem, where we're actually looking at the instead of an individual observation, we're looking at the mean of, say, 25 observations. So if we drew a sample of size 25, what's the probability that the mean cranial length is greater than 190? So notice that I'm using x bar in here now rather than just x. I want to know the probability that the mean is greater than 190. So I'm going to standardize this the same way I did before, except I'm going to have x bar minus mu over now the standard deviation of x bar, and that is sigma over the square root of n, the standard deviation of the sample mean. And that comes from the behavior of the normal distribution. So that is greater than 190 minus the mean, which is 185. And now I'm going to divide that by 12 over the square root of 25. So that gives me probability that the standard normal is greater than 5 over 12 times 12 divided by root 25. So that is equal to the probability that a standard normal random variable z is greater than 5 divided by 2.4. And that is the probability that the random variable z is greater than 5 divided by 2.4 is 2.0833. Looks like that 3 is repeating, so we could probably put a line above that. And now what we'll do is we'll just come to our distribution calculator, put in a standard normal distribution. Probability z is greater than 2.083333, and that is equal to 0.186. So there is that probability that the mean is larger than 190 because of this dividing by the square root of n. The distribution of the sample mean is much narrower than the distribution from the original normal population. So it puts us further out in that tail of that normal distribution, and there's less area that's above 190 when we're talking about the distribution of the mean. Okay, another interesting example here is using the normal distribution to find cut points. In all of the previous examples we've done, we've been looking at finding probabilities associated with particular z values. Now, in this example, we will find a z value that's associated with a particular probability. So students are judged in a poster competition on campus. The scores of the posters are normally distributed with a mean of 70 and a standard deviation of 10. If we stipulate that students who score in the top 5% will win a prize, let's find the score that separates prize winners from those that will not win a prize. Okay, so the probability that the standard normal random variable is above some quantity z naught, we want that to be 5%, 0.05. And we can note that that implies that if there's 5% of the area above it, then there's 95% of the area below it. So we could look at that from a couple of ways. Now, if I want to come over here to my distribution calculator, I can get to this answer fairly quickly just by giving it a mean of 70 and a standard deviation of 10. And then I'm going to select this option to input a probability and calculate a value. And I can calculate the lower tail, the right tail, upper tail, a central probability, or two tails probability. I want the area, I'm looking for the cutoff that separates the top 5% from the bottom, the lower 95%. So this is the one that I want. And I'll put in 0.05. And so that score is going to be 86.4485. Uh, 86.4485. And you can probably round that to 2 or 3 decimals there. Okay, so this introduces the idea of using the other type of calculation where we input a particular area from this normal distribution, and it gives us the x value that's associated with that. So if we standardize this, this is the probability that x minus mu over sigma is greater than some x that we don't know yet, minus 70 over 10. It's a standard deviation. And we want to set that equal to 0.05. Right? That's the probability that a standard normal random variable is greater than some quantity that has 0.05 of the area in the upper tail. And so if we're to use our distribution calculator, I can put in 0, 1 here for our standard normal. I'll specify that I have 5% in the upper tail. That gives me a value of 1.645. For that z value. And so now by my standardization process, I know that 1.645 is equal to x minus 70 over 10. And I can do a little bit of algebra to actually figure out what the score on the poster needs to be to separate the top 5 from the bottom 5. So I'll do a little bit of algebra there. I'll get 1.645 times 10 plus 70 is equal to that x. So I have 70 plus 16.45, and that gives me 86.45 is x, which is what we found on that previous calculation. Okay, let's look at another example of the central limit theorem, but as it applies to proportions. And it turns out that proportions can be thought of as averages of zeros and ones, and so they can be normally distributed, and they also follow the central limit theorem. And the central limit theorem says if the sample size is large enough, then they will be approximately normally distributed. So how large is large enough for a proportion? Well, it turns out that if n times p is greater than 5, and n times the failure probability, 1 minus p, is greater than 5, then the central limit theorem will usually be applicable in those cases. So we'll just do a quick check to make sure n times p and n times 1 minus p is greater than 5. So let's look at an example. We'll note that as we try to standardize sample proportions or probability calculations from sample proportions, we'll be using the standard error of the sample proportion. Okay, so this is the sample proportion, p hat, and this is the population proportion, and this is the standard error of p hat. We'll notice a lot of similarities for these test statistics. This is what we're calculating here is known as a test statistic, and they all have sort of the same flavor to them, where they're measuring a distance between what was observed in the sample and what's hypothesized in the population, divided by the standard error of our sample statistic. In this case, that's the proportion. Okay, so let's take a look at this example. In the mid-1970s, according to the National Center for Health Statistics, 19.4% of all U.S. adult males were obese. What is the probability in a simple random sample of 150 people from this population the percent obese will be less than 15%? So is it reasonable to apply the central limit theorem? So the first thing we'll do is we'll take n times p and n times 1 minus p and see what that gives us. So n times p is our 150 times the success probability here is 0.194, So that gives us 29.1. And n times 1 minus p is 150 times 0.806, and that gives us 120.9. So both of those check out. We can apply the central limit theorem here, and so this is going to be equal to p hat minus p over the square root of p times 1 minus p over n, less than 0.15 minus p which is 0.194 over the square root of 0.194 times 1 minus that, it's 0.806, all divided by 150. So that is equal to the probability that a standard normal random variable is less than negative 0.044 divided by 0.03228. That's equal to the probability that a standard normal random variable is less than negative 1.363. And so now with that, I can take that into my distribution calculator for a standard normal. I'll be looking to calculate a value, some probabilities given a value. So the probability that x is less than or equal to negative 1.363, and that is equal to 0.0864 is the probability that p hat is less than 0.15. Okay, thanks for watching.